We know human civilization extends back about 12,000 years, but Earth itself is more than 4.5 billion years old. That leaves an almost unimaginable span of time. Billions of years in which something extraordinary could have risen and fallen before us, leaving faint or no traces behind. Recent 2025 sediment and seismic surveys, such as the discovery of massive buried sand mounds beneath the North Sea, show how new imaging continues to reveal hidden structures beneath the surface. If humans vanished today, most buildings and machines would collapse or corrode until unrecognizable within thousands to a few million years. What would remain are the chemical fingerprints, plastics, radionuclides, altered carbon, from which geologists might one day reconstruct our presence. We'll look at what modern geology and 2025 tools can and cannot reveal, and which chemical signatures might survive across vast timescales. This video will define the hypothesis, explore the durable clues geologists search for, examine the newest discoveries, and ask what those findings suggest about both forgotten pasts and our own future legacy. The core idea of the Silurian Hypothesis. The idea at the center of this discussion is the Silurian Hypothesis, a proposal born out of the scientific literature on astrobiology.
At its core, it does not claim that an earlier industrial civilization did exist, but instead asks a tightly defined question. If such a civilization had once arisen on Earth, would it still be detectable in the geological record millions of years later?
By framing the issue this way, the hypothesis treats civilizations not as isolated accidents, but as potential repeating phenomena within a planet's history. In fact, some researchers note that it reimagines part of the Drake equation, the formula used to estimate the number of intelligent civilizations in the universe, by considering that multiple epochs of industry could occur even on the same world. The result is less a speculation about lost empires and more a testable inquiry into what planetary scale industrial activity would leave behind after deep time has reshaped everything. A constraint immediately comes into view when geologists consider the mechanics of Earth itself. Because of erosion, subduction, and the recycling of the seafloor, direct archaeological evidence much older than a few million years is exceedingly unlikely to survive. Researchers point out that once you move beyond about 4 million years into the past, the chance of finding intact artifacts such as buildings, tools, or machines drops to almost zero.
This recognition sets a practical boundary for the discussion. Any search for evidence of earlier industry must rely less on physical remnants and more on indirect, chemical traces locked deep in sediments or preserved in isotope ratios.
From that perspective, a question emerges: what detectable planetary scale changes would any advanced industrial species leave behind? And could those changes persist long enough to be studied today? It is one thing to imagine earlier species building machines or cities, but the scientific challenge is more specific.
It is about identifying signatures distinct enough to separate industry from the host of natural forces shaping the planet. The Paleocene-Eocene thermal maximum (PETM) provides a caution here. Around 56 million years ago, the Earth underwent a sharp warming event marked by a dramatic release of carbon and a corresponding shift in isotope ratios.
To modernize, that spike resembles the chemical fingerprint of industrial carbon emissions. But the PETM was entirely natural, likely triggered by volcanic activity or the destabilization of methane hydrates. The resemblance to our own industrial signal shows how easily nature can mimic what we would expect from intelligent activity. This means that if we ever did detect an anomaly, one marker alone would not be convincing. Multiple independent lines of evidence are required to support any such claim. Thinking of our own species highlights the challenge further. Millions of years from now, anyone searching for traces of humanity would not find intact skyscrapers or highways. Concrete breaks down within thousands of years, steel rusts away, and even plastics only leave chemical residues rather than recognizably shaped artifacts. Fossilization itself is an uncommon event. Entire species can vanish from the record without leaving behind a single preserved skeleton. Scaled up, the odds of machines, infrastructure, or even bones surviving tens of millions of years are slim. This leads directly back to the point of the hypothesis. Instead of looking for recognizable remnants, the search must target signals embedded chemically in soil, rock, or ocean sediments. Examples of what counts as durable signals are increasingly clear in 2025. A layer enriched with byproducts of plastics, even after degradation, could still be recognized through unusual molecular fragments bonded in the sediments. Long-lived radionuclides created through artificial nuclear reactions could persist as faint signatures in certain layers of rock. And perhaps most robust of all, the redistribution of carbon and nitrogen isotopes created by large-scale fossil fuel burning or agriculture could leave traces that last for hundreds of thousands or even millions of years.
These signals would never appear as monuments or machines, but as subtle markers that a large-scale industry once rearranged planetary systems. Advances in technology have made this kind of search possible. A few decades ago, the best methods available could barely distinguish natural carbon fluctuations from industrial ones, and what little was known about human-made emissions was still being pieced together. Now, with high-resolution mass spectrometers and refined isotope analysis, measurements can be taken with astonishing sensitivity down to parts per billion. Entire archives of ocean cores drilled decades ago are being re-examined, this time with tools that can parse out details invisible in earlier studies. Sediment layers once cataloged as ordinary mineral deposits are being revisited, and in some cases scientists do identify small but striking anomalies that demand explanation. Machine learning tools now assist in identifying patterns in these chemical records, combing through vast amounts of data to flag unusual constellations of isotopes or compounds that could signal non-natural origins. The most important shift is conceptual. The Silurian hypothesis has moved beyond being a curiosity or a metaphor. It sets out a series of testable predictions. It asks whether chemical residues created by industrial activity, carbon imbalances, persistent radionuclides, synthetic molecules could remain detectable after vast spans of geological time. These questions are then tied to concrete analytic protocols, where every positive anomaly is followed by the challenge of separating natural from artificial causes. Events like the PET ensure caution, demonstrating that natural forces alone can produce signatures strikingly similar to our own impact. Only by looking for patterns across multiple independent markers can researchers avoid drawing false conclusions. This new focus also highlights an unresolved tension. Suppose future analysis of a sediment core were to reveal a sudden jump in carbon isotopes alongside unusual concentrations of heavy metals and long-lived radionuclides. Would that be enough to suggest an earlier advanced species, or could it still be the result of volcanic outpourings and asteroid collisions? Part of the difficulty is that geological catastrophes often distribute materials globally in ways not unlike human industry. The challenge for current researchers is to establish criteria clear enough to distinguish these cases even when the signals are faint and ambiguous. Even with these limitations, the Silurian hypothesis has achieved something significant. It shifted the conversation away from speculative storytelling and grounded it in the realities of geochemistry and planetary science. By doing so, the hypothesis transformed a question that once belonged to science fiction into a framework for interpreting the deep past of our own planet. That science remains cautious and probabilistic, but it stands as an example of using current knowledge to probe questions usually left to imagination. What remains uncertain is scale. Our own presence is so recent that we can still see highways, cities, and industrial waste with our eyes. But if the framework is correct, much of this would vanish quickly compared against the vastness of geological time. Which leads naturally to the question, if all physical traces fade so rapidly, how long does any evidence of us truly last? The fragile timeline of evidence.
The fragile timeline of evidence begins with recognizing just how quickly our most powerful creations disappear. A skyscraper or bridge feels permanent on a human scale, but without constant maintenance, these structures yield to decay within centuries. Concrete splits, steel rusts, glass shatters, and vegetation forces apart whatever remains. What once identified a city becomes, within a few thousand years, scattered debris almost indistinguishable from a natural rockslide. Against geological time, permanence collapses into brevity. Plastics may seem more durable, yet their resilience only shifts the form of their decay. Sunlight and saltwater fracture polymers, grinding them into countless microplastic shards. These fragments settle into sediment, no longer recognizable as objects, but leaving faint chemical residues. Even encased in rock, plastics do not preserve their original shapes. Instead, they leave behind distorted molecules, an invisible layer analyzed only with sensitive instruments. Machines and electronics fare even worse. Silicon chips, glass screens, and circuit boards crumble to dust within decades. In orbit, satellites eventually decay, burn in the atmosphere, or fragment until invisible. On the grand timeline of Earth, the era of technology would vanish with startling speed. Geology makes this disappearance even more certain. Wind, rivers, glaciers, and volcanic eruptions erase exposed surfaces relentlessly. Coastlines shift, mountain ranges rise and fall. Most decisively, the ocean floor renews itself. As continental plates dive into the mantle, sediments and even buried artifacts are dragged down, melted, and reabsorbed. Only in rare, isolated conditions can fragments escape. Fossils form under precise circumstances: rapid burial, low oxygen, minimal disturbance. Industrial traces would require a similar look, yet most would be eroded, scattered, or subducted before fossilization could even begin. Because Earth constantly remakes itself, studies have tried to estimate how long civilization's evidence might be measurable. Early conjectures suggested 10 million years might erase almost everything.
More refined models in recent research now give a sharper window. Most recognizable structures are effectively gone within 1 to 5 million years. Beyond that, the survival of buildings or machines is nearly impossible, though isotopic or chemical fingerprints could endure far longer in sediments not disturbed by tectonics.
In geological terms, our mark on the surface is shallow compared to the vastness of planetary cycles. The contrast with the fossil record of life highlights this fragility. Dinosaurs ruled Earth for more than 160 million years, yet they remained surface unevenly, often as partial skeletons or scattered footprints. Vast populations left only fragmentary evidence. If colossal organisms become scarce in stone, then a civilization existing for much shorter spans would fade even faster. What lasts is not architecture or machines, but shifts in chemistry, carbon isotope spikes, unusual metal signatures, or molecular residues strange enough to stand apart from natural baselines. Chemistry offers one more sliver of permanence. Some artificial isotopes created through nuclear activity possess half-lives stretching into tens of millions of years. Plutonium-244, with a half-life of about 80.8 million years, and Curium-247, lasting roughly 15 million years, would remain detectable if deposited widely enough. While none are presently known in ancient rocks, they illustrate the kind of unique markers that, if found, could confirm industry at planetary scale, even after eons. In contrast, less durable materials like copper wiring, plastics, and concrete vanish or transmute in far shorter intervals. These projections outline the narrowness of civilization's survival curve. At 1 million years, remnants become rare. By 5 million, the probability they persist declines to near zero, except for isolated isotopic anomalies or subtle chemical shifts in sediment. Stretch further into the timeline, and only those long-lived markers have even a chance of whispering that industry once existed. The difference between eras we can still study and epochs already erased is measured in layers of buried soil and centuries of tectonic movement. This brevity reframes both past possibilities and our own legacy. If another advanced species rose before humanity, its constructions would likely rest within the same fragile bracket, erased in a few million years, reduced to chemical peculiarities in stone. For our species, the lesson is the same. Skyscrapers, highways, and machines exist only as temporary monuments. What may survive deeper into time are thin strata showing altered carbon cycles, unusual concentrations of metals, or traces of synthetic molecules. Large-scale construction is fleeting, but chemistry can carry faint signatures far further. Recognizing this, the investigation cannot rest on artifacts. Those fade too soon. The realistic question becomes where subtle evidence hides, how to identify it, and how to distinguish it from natural processes capable of producing similar signals. That step turns attention away from ruined buildings and broken machines towards something else, the record beneath our feet, carried silently in stone. Searching the rocks for industrial clues. When the surface world fails to preserve, researchers turn to stone for the traces of change. Sediments and layered rock carry a chemical record of Earth's history, storing the remnants of atmosphere, climate, and catastrophic events over millions of years. If an industrial civilization once emerged before humanity, its presence would most likely survive not as buildings or machines, but as shifts locked into isotopes, metals, and molecular residues. The challenge is learning how to tell apart what only industry could create from what nature itself routinely imitates. Some markers rise above the rest.
Geologists now focus on 4 concrete proxies. First, stable carbon isotope excursions, delta TVIRS, delta 30C, which reveal abrupt shifts in the balance of carbon-12 and carbon-13, patterns that fossil fuel combustion leaves differently than volcanic outbursts. Second, nitrogen cycle shifts, delta 15, recording imbalances caused by artificial fertilizers rather than marine blooms alone. Third, anomalous heavy metal ratios and distributions, lead, copper, cadmium, mercury, whose concentrations and transport patterns betray industrial activity more than regional eruptions. Fourth, persistent synthetic molecules and breakdown products, such as plastic fragments or halogenated organics, which have no direct natural counterparts. Each of these signals can persist in sediments and provide testable, measurable evidence of disturbances beyond ordinary geology. Yet these markers exist against a backdrop of powerful natural mimics. Large igneous provinces, where tremendous volcanic outpourings cover continents, can overwhelm the climate and leave deep carbon isotope excursions.
Volcanic intrusions into organic-rich deposits can release carbon dioxide and methane in pulses that look industrial at first glance. Methane hydrate releases from the seafloor likewise generate sudden warming episodes, while asteroid impacts scatter rare metals like iridium and shock the climate in ways that ripple through isotopes. Events such as the Paleocene-Eocene thermal maximum or various oceanic anoxic events demonstrate how natural processes alone can leave signals that, if viewed in isolation, might be mistaken for technosignatures. This makes it essential to treat any one anomaly with caution. The real advance today lies not in single measure detections, but in multiproxy correlation. Researchers combine isotope geochemistry, trace metal mapping, organic molecule fingerprinting, and cross-site correlation to isolate anomalies that refuse to match known patterns from volcanism impacts or methane release. A lone carbon spike might be volcanic, but if it appears alongside industrial-type metal ratios and synthetic organics, stretched across multiple global sites, the case strengthens substantially. The guiding principle is simple. Industry spreads multiple kinds of chemical change at once, creating a web of linked markers. Keep listening. We'll show what geologists are actually scanning for. Carbon isotopes remain a primary proxy. Humans today have changed the balance of delta 30 by releasing vast amounts of light carbon from fossil fuels. The geological fingerprint is distinctive. Volcanic eruptions alter isotopes too. but in slightly different ways. The isotopic swing has its own character depending on the source carbon. Sediment cores sampled today are checked for ancient shifts of the same kind and with similar abrupt timing. A rapid global decline in delta A1-stained sediments would be a starting point, not proof in itself, but a flag to look closer. Nitrogen isotopes add a second dimension. Industrial fertilizers alter delta 1:15 ratios, leaving unusual imprints in soils and marine sediments. On regional scales, natural processes such as algal blooms can shift nitrogen isotopes, but global coordination and abrupt signatures hint at something larger. By assessing delta 15 anomalies across continents, scientists can distinguish between localized ecologies and planet-wide industry. If paired with a sharp delta 30C anomaly, the coincidence is far harder to dismiss as mere happenstance of nature. Metals contribute further evidence. Elevated mercury levels are often tied to volcanic events, but unusual combinations and concentration patterns matter. For instance, lead and copper clustering around certain layers could signal extraction and processing far beyond natural scatter. Researchers map vertical and lateral distributions of these metals across multiple drill cores. It is not the presence of a single element, but the ratio set alongside its spread that keeps the industrial hypothesis alive. Synthetic molecules provide perhaps the clearest distinction. Plastics, even as they decay, leave fragments of unique polymer residues. Modern tests show these fragments bond with sediments and withstand heat and pressure. Likewise, halogenated organics, chemical compounds useful in refrigeration and solvents, persist in ways no natural biochemistry generates. Laboratory simulations catalog how these substances transform under geological conditions. With that database, scientists scan older sediments for matches. A confirmed find would be difficult to explain without deliberate synthesis. Still, mimicry shadows each line of evidence. Ancient volcanic provinces, methane bursts, and asteroid shocks can create steep delta 1:130C declines. Intrusions of magma through carbon-rich deposits can mimic massive fossil carbon release. These natural paths complicate every readout.
For this reason, modern protocols insist on using multiple proxies together. One illustrative criterion researchers now cite is this: A.
Global abrupt delta 30C decline, paired with anomalous industrial-type metals and synthetic organics, would be far harder to explain by volcanism or impacts alone. It is not the signal, but the overlap of signals that matters. Methodologically, the process has grown sharper. Sediment drill cores only centimeters wide contain hundreds of thousands of years of chemical history. Advanced spectrometers now analyze with precision down to parts per billion. Each layer is logged against established baselines for known events, volcanic crises, asteroid impacts, methane releases, before deviations are considered significant. By 2025, artificial intelligence aids the search, scanning patterns that humans might miss. But interpretation remains a human task, balancing possible natural explanations against the hypothesis of industry. Progress also depends on international cooperation. No single drill site offers enough coverage. Samples from Asia, Africa, North America, and the ocean floor all feed into the comparison. With multiple sites, researchers can separate local oddities from true global signatures. If an anomaly repeats across continents, the chance of coincidence drops. Only then does the hypothesis advance from speculation to measured inference.
In the end, the rocks do not hold artifacts recognizable to the eye. Instead, they preserve needles of difference, isotope excursions, shifted nitrogen balances, clustered metals, or organic residues out of place. These subtleties are fragile in signal yet sturdy in endurance, capable of surviving millions of years.
The question remains whether those subtleties will ever converge into a pattern that nothing but industry can explain. And if there is any place on Earth where such a pattern might be preserved most faithfully, it is in the least disturbed archive of all: deep ocean sediments and the hidden archive. Beneath the world's oceans lies an archive different from anything preserved on land. The seafloor steadily gathers layer upon layer of fine particles, Dust carried by winds, microscopic shells from plankton, molecules from rainfall, traces of volcanic eruptions, even chemical byproducts drifting down from the atmosphere. While continents are scraped and recycled by weather, glaciers, and the motion of tectonic plates, many deep ocean basins accumulate record after record for millions of years. These sediments do not hold monuments or skeletons, but they preserve sequences of time pressed into thin layers that scientists can read with remarkable precision. Yet even this global reservoir has its limits. The crust of the oceans is younger than the continents. Because seafloor spreads from mid-ocean ridges and dives back into the mantle through subduction, few sediments older than about 170 million years survive. Any continuous archive of earlier ages before the Jurassic is gone. What remains of younger intervals is patchy, shaped by where basins escaped burial or tectonic disturbance. This makes every surviving core from the deep ocean precious. It is one of the few ways we can test not only natural upheavals in Earth's history, but also, in principle, whether signs of industry might once have been recorded and preserved. Accessing this archive has proven difficult on a practical scale. The seafloor covers more than 2/3 of Earth, but only a scattering of places have ever been drilled deeply enough to recover long sediment cores. Programs such as the Ocean Drilling Program and its successor, the International Ocean Discovery Program, have provided almost all of this material.